At the end of the last unit, you got introduced to something called the mole. And we said that the mole was kind of analogous to a dozen, where a dozen is 12 of something. A mole is 6.02 times 10 to the 23rd of something. So the idea is that instead of having to give a total number of individual particles, which would be really awkward because it's huge numbers, we're able to just bundle them up and say, okay, we have 1 mole of this or 2 moles of that or something, and that gives us an exact number of particles that we can work with. Now, the question ought to be, well, why that number? Like, why do we decide to bundle them up in such a strange number like that? And the answer is actually a really good answer because it allows us to deal with ratios, and it allows us to easily calculate the amount of mass in 1 mole of any material, and therefore the amount of mass in any number of moles of any material. So it's a very easy way to get back and forth between the number of particles and the number of grams, which is something that we sometimes need to do. And that will happen a lot more in the next unit. But for now, we're just going to lay the foundation here. So Avogadro came up with this number because 6.02 times 10 to the 23rd is equal to the number of carbon atoms in exactly 12 grams of carbon 12. Now, we have to specify carbon 12 because there are other isotopes of carbon. So we have to say we're dealing with this isotope of carbon where every single atom has a mass of 12 AMUs. So a little review here. Back a long time ago, we learned about the structure of the atom, and we learned that inside the nucleus there were protons and there were neutrons. Each proton has a mass of 1 AMU. Each neutron has a mass of 1 AMU. So if we count up all those particles, we get the total mass for the atom. And we learned that we could just go to the periodic table and get the atomic mass off of that little block on the periodic table. And that would tell us the mass of the atom, or at least of the most common isotope. And then we can also get from the atomic number how many protons there are. So by subtraction, we can figure out how many neutrons there are and so forth. So anyway, we want to deal with carbon 12 here that's got 6 protons and 6 neutrons in it. And as it turns out, if you collect up 12 grams of that, it has this many atoms in it. And we're not going to go into how we figured that out, but just trust me, it does. Now, the neat thing about that is that because he chose 12 grams of carbon 12, we can kind of use ratios to figure out how many grams of other things are in 1 mole. And let me show you how that works. Let's say we want to compare hydrogen to carbon. So we have 1 atom of hydrogen compared to 1 atom of carbon. So if you look on your periodic table, you'll see that the atomic mass of hydrogen is 1 and the atomic mass of carbon is 12. So we have, if we're just dealing with 1 atom of each, we have a mass ratio of 1 to 12. Now think with me logically and say, well, what if I had 2 atoms of each? Well, that would make this 2, and that would make this 24. Here, we'll do this. Hydrogen 1, carbon 12. That way the numbers are up here for us to look at. So this has a mass of 1, this has a mass of 12. If I use 2 atoms, it will be a 2 to 24 ratio, which still reduces to 1 to 12. Now, hopefully you are familiar enough with ratios to be able to follow my logic when I say it doesn't matter how many atoms I have. If I have 100 atoms of this and 100 atoms of this, the ratio will still be 1 to 12. If I have 1,000,000 atoms of this and 1,000,000 atoms of this, the ratio will still be 1 to 12. Well, if I have this number of hydrogen and this number of carbon, the ratio is still 1 to 12, right? The mass ratio will still be a 1 to 12 ratio. Well, we've already established that for carbon, this number of atoms gives 12 grams. Therefore, for hydrogen, this number of atoms must be 1 gram. right? Because now we're using a different unit. We're using grams instead of AMUs, but the ratio has to be the same. So if this number of atoms of carbon weighs 12 grams, and we know the ratio is always going to be 1 to 12, this number of atoms of hydrogen has to weigh 1 gram. Now we can substitute any element on the periodic table. Let's say that we want to do nitrogen. 1 atom of nitrogen. And if you look on your periodic table, you'll see that the mass is 14. And so we want to make sure that we are specifically talking about that isotope because there are other isotopes. So that's a 14 to 12 ratio. Okay, using the same logic, we could say that if I use 2 atoms of each, the ratio will still be the same. If I have 1,000,000 atoms of each, the ratio will still be the same. If I have this number of atoms of each, the ratio will still be the same. And therefore, if this number of atoms of carbon has a mass of 12 grams, then this number of atoms of nitrogen has a mass of 14 grams. So what that means to us is that we can look on the periodic table. We can take any element we want, and we see on there an atomic mass that gives us the mass of that atom in AMUs. And we can say, well then, the mass of 1 mole of those atoms would be that same number in grams. So let's do a couple of examples. We're going to call this molar mass. The mass in grams of 1 mole, 6.02 times 10 to the 23rd particles of a substance. So I'm going to say particles because we're not always dealing with just atoms. Sometimes we might be dealing with molecules or formula units or ions or anything we want. But the mass in grams of 1 mole of that substance is called the molar mass. How much mass does 1 mole have? So we can go to the periodic table and just get those numbers. Now let's say that we wanted to do a molecule, something like carbon dioxide. Then we would look at each individual atom separately. And you remember doing this back when we had to calculate formula masses. So if I wanted to calculate the formula mass of this, I would say there's 12 AMUs for each carbon, for the carbon. There's 16 AMUs for each oxygen, so we'll have 2 oxygens, so 2 times 16. And so that's going to be a total of 44 AMUs. 1 atom of this has a mass of 44 AMUs, 12 in the carbon and 16 in each of the oxygen. Now, if we want to talk about a whole mole of that, then we can say that there's 44 grams per mole. And that's how we do molar mass, the number of grams per mole. It's the same number. So that makes it very easy to calculate the mass of 1 mole of material, since we can easily use these ratios. You know, and you don't have to stop and remember every time that this is a ratio, as long as you know that all you have to do is go to the periodic table, pull off the atomic mass, and that automatically becomes the molar mass, as long as you change the unit to grams. So let's say that we want to get back and forth a little bit. I'm going to give you a little chart here. And let's say it will always come back to moles. We want to get to the mass sometimes. Sometimes we know the number of moles and we want to get to the mass. Sometimes we know the mass and we want to get to the number of moles. Sometimes we want the number of particles. Now we know that in 1 mole, there's always 6.02 times 10 to the 23rd particles. So that would mean if we know how many moles we have, we just have to multiply that times 6.02 times 10 to the 23rd. In other words, if I have 2 moles, it would be 2 times this number for the total number of particles. If I have 10 moles, it's 10 times that number. If I have a half a mole, it's half of that number. So along this arrow, I would just say times 6.02 times 10 to the 23rd. So to get from moles to the number of particles, we're going to multiply by Avogadro's number. Now you've taken enough math to probably figure out that the opposite requires the opposite operation. So if we want to go from the number of particles to moles, we would divide by 6.02 times 10 to the 23rd. Now think for a minute, something more familiar. You probably learned how to do this in the 3rd grade or something. If I gave you 500 eggs and I asked you how many dozen is that, you would automatically know divide by 12. You wouldn't even have to think twice about that. And this is the same kind of operation, it's just a different number. So if you have your total number of particles and you want to know moles, you'll divide by the number of particles in a mole. So that's how that goes like that. Now between moles and mass, we have to use the molar mass, which we talked about just a minute ago. So the molar mass is the amount of mass in 1 mole. So if we're trying to get from moles to mass, we would multiply by, I'm just going to write mm, and we'll say down here mm is equal to molar mass. So if we have 1 mole, then the mass is simply the molar mass, right? It's the mass of 1 mole. If we have 2 moles, it'll be twice the molar mass. If we have half a mole, it will be half the molar mass. Hopefully that makes sense. And then if we want to go the opposite way, of course we'll have to divide by the molar mass. And when we get into the next unit, we'll be doing a lot of that because usually we know how many grams we have because we can weigh that out. And then if we divide by the molar mass, it tells us how many moles we have, and then we can deal with the number of particles, which actually is going to become very important to us as we do other kinds of problems later on. So let's say that we try a couple of examples here so I don't leave you hanging too badly. Let's say that we're given 1.4 times 10 to the 24th atoms of something. Oh, let's say they're atoms of CO2, why not? And that would be molecules of CO2, wouldn't it? Okay. And let's say that we would like to know how many moles that is and what the mass is in grams. So we'll do 2 things with this. So we know how many molecules, and if we divide by Avogadro's number, so remember, this is very similar to that thing where if you know how many total somethings you have and you want to find out how many dozen, you would divide by 12. If you want to find out how many moles, you divide by the number of particles in a mole. Now, just in case you've forgotten how to use your calculator, this is where you use that EE button. So I'm going to type in 1.4 EE24. Remember, we don't put any tens in. And then I'll say divided by 6.02 EE23. And that gives me, let's see, according to this I can have 2 significant figures because this has 2 and this has 3 and I have to go with a smaller number. So that's going to be 2.3. All right, now if I want to know how much mass that is, how much does this weigh, I have to know how much 1 mole weighs. And we just figured that out a minute ago. It was 44, right? So every mole of carbon dioxide weighs 44 grams. I have 2.3 moles. So 2.3 moles times 44 grams per mole gives me 102, and I can only keep 2 significant figures. Well, that's a pain. So now I'm going to have to say 1.0 times 10 squared. That's the only way to get my 2 significant figures. And it'll be that many grams. So about 100 grams of carbon dioxide I have there. Let's do one more problem before I quit here. Let's start with the number of grams of something and go backwards. So what if I am given 15.0 grams of argon? One of my favorite things. Okay, let's say that I want to know how many moles this is and how many particles. You always have to go to moles first. So you never can get directly from mass to number of particles or vice versa. You've always got to go to moles in between. So if we're going to take 15.0 grams, I'm going to divide that by the molar mass of argon, which I don't happen to know off the top of my head. 39.9. Oops. 39.9. And that's grams per mole. So 15 over 39.9. Calculator. That gives me 0.376. And that's the number of moles in that sample. Now, if I want to know the number of particles, each mole has 6.02 times 10 to the 23rd atoms. So we're going to take 0.376 moles, multiply it by 6.02 times 10 to the 23rd, and this will be the number of atoms per mole. So times 6.02 EE23 equals 2.26 times 10 to the 23rd atoms. So there's a couple of examples to get you started.